My name is Shubhartak Sankharsh, a Master's of Artificial Intelligence and Machine Learning student at Adelaide University. Today, I'm presenting my final presentation for my capstone project titled Learning Action Conditional World Model for Autonomous Navigation in Robotic System, which is supervised by Professor Peng Shi and Dr. Bing Yang. In one sentence, this project builds a lightweight world model that lets the robot imagine the future before it moves, paired with a planner that searches those imagined futures for the safest action, trained with entirely in simulation, and then repeated on real Unitree Go2 robot. That sim to real journey is the spine of everything I will show you today. So here's the plan. I start the research with my 3 research problems and the research questions and how the study is designed. Then I walk through the methodology, the world model architecture, how the data was collected in simulation and on real robot, and then how the planner was basically 4 iterations. From there, results are into 2 parts, part A in simulation, part B on real Go2. I will close with an honest conclusion and then hand over to a 5-minute live code walkthrough. So, robots, wheeled or legged, increasingly have to navigate cluttered, unfamiliar spaces without the pre-built map, relying on both depth and lidar. The dominant approach, reactive reinforcement learning, like PPO, picks an action from the current observation alone. It never imagines what happens before it acts, so it reacts. It doesn't have any plan. So what model flips that? It predicts the future sensor state condition on candidate actions, so a planner can look ahead, score entirely sequence before committing. That's the core idea which project tests end-to-end. Now, coming for the research questions, that gives me 3 research questions. Research question 1 is the prediction. Can a lightweight action conditional RSSM accurately predict a future robot state from onboard depth and lidar? And the research question 2 is planning. Does combining that world model with the CEM planner beats a reactive PPO baseline? And research question 3 is the design choice. Which architectural decision actually matters? Whether it is RSSM versus warm start, image versus feature space, proximity gating, attention, everything today is organized around these 3 questions, right? So the project is split into 2 parts. Part A trains and validates the entire pipeline in simulation. Part B repeats the real data half on a physical Unitree Go2, reusing the identical HDF5 schema. And so the results are directly comparable across all domains. The scale gap is the headline number. Part A logged 617,000 transactions across 5 procedural environments. Part B collected roughly 10,784 transitions across 3 real scenarios: empty room, obstacle, recovery, all in one physical lab room teleoperating a Unitree Go2 EDU instead of a simulated Turtlebot 3. That's about 57 times less the real data, and it actually matters a lot for the results. Now, coming for the system architecture, this is the full system. Sensors, RGB, depth, lidar, robot state, feeds a multi-model CNN encoder that compresses everything into a compact latent. The latent drives the RSSM core, combining a deterministic GRU path with a stochastic latent state to track both what it's sure about and what is uncertain about. 4 prediction heads branch off: an image decoder, a depth decoder, a reward head, and a continued drone or head. Underneath the CM planner, as we can see, a candidate action sequence rolls out through RSSM imagination, scores the imagining into rewards, keeps the best elite set, refines over several iterations, then execute the first action and replans everything around. So now coming for the RSSM core idea, the world model idea, the CNN encoder takes the 64 by 64 depth image and then 24 beam lidar scan and the goal vector and compresses them into an embedding which drives a GRU with a casual self-attention on top, building a deterministic hidden state over time. A separate prior posturicate stochastic latent captures the model's uncertainty. On top sits the decoder, a depth decoder for reconstruction, a reward MLP, and a proximity head predicting minimum lidar. So on training this 4.57 million parameter RSSM Adam W with cosine schedule, 3-bit KLR regularization, sequence length is 16, and I train it in full FP32 mixed precision. Now, for data set collection, for part A, I built a high-speed procedure raycast simulator replicating Turtlebot 3 waffle kinematics and sensor across the 5 maps. And for part B, data comes from the Ethernet-tethered Unitree Go2 EDU driven by a joystick teleoperation with a pre-flight sensor checks every session. All three scenarios were collected in one physical lab room. The room in this photo, as you can see, where I actually worked through the RSSM math on the whiteboard before writing the training code. Both have shares identical HDF5 schema as we discussed before, which makes the cross-domain comparison later for possible. And one last thing is for safety, every real robot runs was capped around 0.25 meters per second linear and 0.8 radians per second angular velocity. Now coming for the planner design. So the CEM planner went through 4 iterations. The old CEM, the CEM version 2, which basically have more what we call goal awareness swarm start. But the collisions was too much. It was increasing dramatically. And then we have added a version 3, which have a hard safety filtering forcing a full stop near walls. And final CEM combines a goal scoring PPO residual warm start, milder safety term, and stuck escape behavior. Now, for part A, the world model prediction results. Starting with the part A prediction, the research question 1 held out validation SSIM climbed steadily, 0.73 at 2000, 0.79 at 4000, and 0.81 at the step 8000, which was my best checkpoint. As you can see the numbers, right? So clearly they're strong enough to support the imagination-based planning. That's an important framing point for the result for research question 2. The bottleneck was never can the model see the future. It was how the planner actually used those imagined futures to choose an action. Now, for part A, you have a dataset analysis, and it is basically I logged 617,000 transition with a 0 corrupted samples, but difficulties from uniform across the 5 environments. And then we have on coverage and sensing the trajectory heat maps compare the pure exploration against PPO rollouts. And that's it. For part A results, the planner evaluation, this table puts number into what we call planner story. The final CEM is basically around 85% success is open, 60 in mixed precision, what we call 45 in clutter, and 25 in corridor, as you can see the numbers. All right. So for part A results, the final PPM is basically the quotient, which leads us that the PPO is still the stronger baseline on the raw success. 95% is still open versus final CEM 85. So this RSSM forecasting quality was never a limiting factor. It was the plan and design, iteration after iteration, that decide the navigation outcomes. Coming to part B results. Basically, training RSSM from scratch on real Go2 data gives a test SSIM about 0.7 overall, and consistently compare it to 8.15 in part A simulation, remembering that numbers comes from roughly 11,000 transitions, which is 57 times less the data. I also tried forms starting from part A weights before fine-tuning on real data essentially have no benefits. The domain shift from simulated depth and real sense depth plus ego motion is too large from warm-up to help. Now, the real data sensors is there to ground what we call real data looks like. These are automated QA previews collection pipeline generates for every session before it enters the data. And then we have part B results for cross-domain transfer. This is one of the clearest findings in this project. I evaluated every model. Part A simulated train, Go2 from scratch, Go2 fine-tune on both sim test and real Go2 test set using the same 300 window open loop SSIM protocol. The pattern is still strong diagonal and a weak off diagonal. For the part A model scores 0.79 on sim but drops to 0.516 on real. The Go2 scratch model is basically 0.69 on real but 0.49 back on sim. Each model fits its own domain, so neither zero shot transfer nor fine-tuning helps, right? So Go2 hardware access ended before true closed loop testing on robots. So I bounded to research question 2 honestly rather than skipping it. A zero shot transfer of the real simulated with match plus a new model heuristic control. So one thing I like to point out is there's a Chrono Dreamer inspired proximity head predicting minimum lidar range and gating unsafe actions. Again, prediction doesn't automatically translate into planning skills. Handwritten heuristic carry most of the practical work without the robot in the loop. So conclusion, putting this all together, to end this, I would say a lightweight action conditional RSSM predict well in simulation. For part A, warm doesn't help, warm up doesn't help, and without the robot closed loop skill is bounded by simulation proxy, where the world model only marginally beats hand over heuristics. So, yeah. So that's everything I wanted to cover. This project took a lightweight world model from procedure, and thank you for watching. And I'm happy to take any questions. This is my GitHub link repo where you can actually navigate and learn more about the my research. Thank you. Let's dive into the code walkthrough. And basically, this is the repository I've created. And it's nothing but just Gazebo RS2 pattern simulation I've set up. And then we have a go-to data setup for data set collection and training. Then we have one model pipeline where we analyze everything. And at last, we have an evaluation CEM planner themes. Now, this is the README file. And let me dive into the main concepts of the code. All right. So basically, this is the loader for the real go-to sessions. And the key thing is to point out is why it exists separately from the Part A dataset class. The doc string at the top, you can see it explains itself that the go-to collector restart every episode ID at 0 in every session. And so a naive loader would collide episode across the files. So coming to what we call go-to sequence dataset. Yep. That's the file which fixes everything by keying every episode on a file room episode ID tuple. Now, this is doing by stratifying the 80-10-10 split, but per scenario, not globally, and it deals episodes longest first into whichever split is furthest below its target share of transition, specifically because real episode lengths are vividly uneven. That's the direct fix for a problem plane random splitting would have caused with this little data. One more thing I will worth showing is that the get item, where I optionally add a small sensor space noise during training, which augment that into greater than 0, as this is the cheapest defense against memorizing individual frames when you only have few thousand real transitions. Now, something similar is called verify go-to, which basically verify the HDF file are not corrupted, and that's the main thing, which let no corrupted file goes into the HDF file, so it keeps the format clean. Now, this is the basically the world model setup, the RSSM training, and this is the whole world model file in one file. So at the top, we can see the dimensions: a 256 unit deterministic state, a 32-dimensional stochastic latent, 3-bit setup to 1.0, and in it points out to three things: the GRU cells that drives the deterministic path, the casual self-attention module layered on top of it, and it's the proximity head that's the chronodremo inspired edition that predicts the closest lidar range. So CEM planner does not reject it, right? And so now coming to the training time method, for every step, it computes a posterior from the real observation and a prior from the hidden state. Now, used only at the planning time. So basically notice it never touches the encoder or real observation again. It just rolls the prior forward step by step, purely in latent space, and returns the predicted rewards. That's the actual imagination in the CEM planner search. Now, coming to the training, and this is the training loop. So the script turns the same RSSM class on the real go-to data. It imports the RSSM.py directly rather than duplicating it, which deliberates. Same architecture, same loss, only the data loader changes, right? And then the evaluate function is one of the highlight because it's where the per scenario SSIM numbers from my results actually comes from. So if you go to the evaluate function, this is the one which do all the work by itself. Now, one thing noting is the CEM planner, which is the final thing for our script. This is the final planner, and it basically doc string at the top. You can see it basically planner evaluation story from the slides in one sentence. It combines CEM plus the goal progress and scoring with V3 PPO warm-up start and the mild, not hard safety terms. Then there are 3 scoring pieces feed into the act goal heuristic rewards. Imagine sequence that close distance to the goal. LiDAR penalty softly discourages the driving into the near front danger zone, and the warm mean seeds then search around the PPO policy and its own prediction rather than starting from 0 every step, which is what makes the search converge fast enough to run in real time. So that's all for it. And that's the core of the pipeline, basically. Schema compatible data loader, one RSSM class shared across the sim and real, a training script that honestly reports per scenario, and a planner that explains about which score is doing the work. Everything else in this repo is just the gazebo style simulator, the PPO baseline, the evaluation scripts, and the builds. It builds exactly on top of all these 4 pieces.